All right, today we are going to try and unravel one of the most fundamental and, let's be honest, one of the absolute weirdest things in the entire universe light. So let's just dive right in. It all starts with a question that sounds super simple, but the answer is anything but. Just think about it. You can look up at the night sky and see a star that's billions of light years away. But what is that light traveling through to get to you? I mean, between that star and your eyeball is just nothing, a vast, cold, empty vacuum. So how on earth does light make that incredible journey? Well, to even begin to solve this puzzle, we have to talk about waves. But, and this is a big but, not the kind of wave you're picturing at the beach. We're talking about a very, very special kind of wave, one that can pull off the incredible trick of traveling through absolutely nothing. So, check this out, because this is really the key difference. On one side, you've got what we call mechanical waves. Think of sound, right? If you clap your hands, that vibration literally has to push air molecules around to get to your ear. So no air, no sound. Simple. But then you've got light. It's an electromagnetic wave, and it plays by a completely different set of rules. It doesn't need a medium. It's a disturbance in the fundamental fields of the universe itself. Wild, right? Okay, so what is this wave that can travel through total emptiness? Let's peel back the layers here. We're going to dissect the anatomy of a light wave to see what really makes it tick.
And here's the official term, an electromagnetic wave. Now, the key words to focus on are oscillating electric and magnetic fields. See, light isn't a vibration of stuff like water or air. It's a vibration of pure energy. And that energy is split into these two components that perform this beautiful, self-sustaining dance through space.
Okay, so here's how that dance actually works. Picture an electric field vibrating, let's say up and down. Well, one of the fundamental laws of physics says that a changing electric field automatically creates a magnetic field. So boom, a magnetic field pops into existence, vibrating side to side, perpendicular to the electric one. But wait, it gets better. A changing magnetic field, in turn, creates an electric field, so they just keep creating each other over and over again, basically leapfrogging through space at the speed of light. They don't need anything to carry them because they carry themselves. They are their own medium. It's incredible. Now, every single one of these electromagnetic waves has a couple of essential properties. And if you can get a handle on these, it's kind of like learning the basic language of light, the language it uses to paint the world with color, to carry energy, and to send information flying across the universe. First up, we've got wavelength. This is super straightforward. It's just the distance from the top of one wave to the top of the very next one. And for the light that our eyes can actually see, this is what determines color. A shorter wavelength looks bluish or violet to us, and a longer one looks reddish. It's really that simple. Color is just how our brains decide to interpret different wavelengths of light. All right, next up is frequency. Imagine you're standing on a dock and you just count how many waves pass by you every second. That's it. That's the frequency. And here's the really important part. The more waves that pass per second, the higher the frequency, the more energy that wave is packing. It's a direct relationship. And here's a mind bender for you. All of these waves, it doesn't matter what their wavelength or frequency is, they all travel at the exact same speed in a vacuum. It's c, the speed of light. And it's not just a speed, it is the ultimate unbreakable speed limit of the entire universe. It's a fundamental constant woven right into the fabric of space-time. And the fact that nothing with mass can ever reach it, well, that changes everything about how we understand reality. All the colors we see, the entire rainbow, that's just a tiny, tiny fraction of what's actually out there. It's just one small part of the whole electromagnetic spectrum. If you take those wavelengths and stretch them way, way out, you get radio waves. Squeeze them a bit, you get microwaves. Keep going, you get infrared, and then you get to our familiar little rainbow of visible light. Squeeze them even tighter, and you get ultraviolet, then X-rays, and finally the super powerful, high-energy gamma rays. But here's the thing to remember. It's all the same stuff. It's all light. Okay, so we've got this self-sufficient wave zooming along at the cosmic speed limit. But obviously, it doesn't just travel in a straight line forever, right? The second it actually runs into some stuff, into matter, that's when things get really interesting. So let's take a look at how light behaves when it's out in the real world. And honestly, you see this stuff every single day. First, you've got reflection. That's just light bouncing off a surface. It's the reason a mirror works. Then there's refraction. That's light bending when it goes from one thing to another, like from air into water. It's why a straw in a glass looks like it's broken. The other two, diffraction and interference, they're a little more subtle, but they are the absolute smoking gun proof that light really does act like a wave. And right when you think, okay, I get it, light is a wave, physics just throws this massive curveball at you, because it turns out light also acts like a particle, a tiny individual packet of energy called a photon. So get this, when it's traveling, it acts like a wave, all spread out. But the moment it interacts with something, the moment it delivers its energy, it does it all at once in a single precise point, like a particle. It's a wave and a particle at the same time. It's both. It just depends on how you measure it. This is the famous and famously weird wave-particle duality. It's one of the cornerstones of quantum mechanics. Now, I know this all might sound like super abstract, weird physics, but understanding this strange wave that sometimes pretends to be a particle, well, it has completely, and I mean completely, transformed our world. Let me show you what I mean. Think about your daily life. That super fast internet you're using, that's data traveling as tiny pulses of light through fiber optic cables. Your Wi-Fi, your cell phone signal, the radio in your car, all of those are just different flavors of electromagnetic waves. Lasers that are used for everything from surgery to scanning your groceries, medical x-rays that can see inside your body. All of this incredible technology exists because we figured out the physics of light. So let's bring it all back to that first question. The big takeaway is this. The puzzle of how light crosses the vacuum of space is actually solved by light itself. It doesn't need anything to travel through because it creates its own path. It is its own medium. Just this beautiful, unstoppable, self-sustaining dance between an electric field and a magnetic field, zipping through the cosmos until it finally runs into something, like the back of your eye. And that leaves us with one final and maybe even more profound question to chew on. Think about it. We know an ocean wave is just water that's waving, and a sound wave is just air that's waving. But if a light wave can travel through a perfect vacuum where there is literally nothing, then what exactly is waving?